welcome to our Physics 135A tutorial video. We're currently looking at slide 12 of the Unit 1 lecture notes, where we're evaluating things like acceleration, velocity, position, and time. In this case, the question says a particle moves along the x-axis according to the given function, which is 10 times the time minus 2 times time squared. So that's x is a function of time, or the position is a function of time. Notice that's a negatively oriented quadratic. There is acceleration, because when position is a quadratic function of time, that means the slope is changing, so by definition there is acceleration. So we're asked, where is the particle at 3 seconds, and then what is the average velocity over the time interval 0 to 3 seconds? So we're going to switch over to a blank sheet of paper, and our x as a function of time is 10t minus 2t squared. Let's double check. Yeah, 2t squared. And so first of all, where is the object when time is equal to 3 seconds? So that's 10 times 3 minus 2 times 3 squared. That's going to be 30 minus 18 meters. And so we get 12 meters for the position of the object at 3 seconds. So let's look at the answers. I think this answer is eliminated, and so is that one, because B and C do not have the correct position for the system at 3 seconds. It should be 12. So it's down to A and D, but the choices for the velocity are 4 meters per second and 12 meters per second. So we're going to have to calculate the average velocity. The average velocity is x final minus x initial over t final minus t initial. You can think of that as delta x divided by delta t, or the slope of position. What is x final? We know x final, we just calculated it. What's x initial? Well, what's t initial? T initial is 0 seconds, and so we're going between 0 and 3 seconds. So t initial is 0, but if you place a 0 for t, then you get 0 minus 0 here. And so I think overall the position is 0 if you place 0 for the t variable there. So that means that x initial is 0, x final is 12 meters. 12 meters minus 0 meters, that's the numerator. I'll scroll down. T final is 3 seconds and then 0 seconds. So this works out to be 4 meters per second. So the correct answer would have been A in this case, 12 meters position at 3 seconds and then 4 meters per second for the average velocity. But if we go to the next problem, it's the same system moving in the same way from the prior exercise, but now we're changing the time interval, so 2 seconds to 3 seconds. What is the average velocity in that period? So we'll calculate the V average in the same way, and that's x final minus x initial divided by t final minus t initial. T final is still 3 seconds. T initial now is 2 seconds. If t final is 3 seconds from the prior problem, x final is still 12 meters, but we need to know what is x initial, because now the t initial is different, and so we need to plug in x initial right here, but we don't know yet what that is. And so if we look here, what would happen if we plugged in 2 seconds for t? Well, we would get, let's copy the formula down here, x of 2, that's 10 times 2 seconds minus 2 times t squared, but if t is 2, then we'll find 20 minus 2 cubed is 8, so 20 minus 8, that's actually 12 meters. So our x initial is 12 meters, and so our V average will be 12 meters minus 12 meters. You may have already caught on what's about to happen. T final is 3 and the T initial is 2. these are seconds, and so you get 0 meters over 1 second. So actually the average velocity is 0 meters per second. But how is that possible? Because we know that if we look over a different time interval, there is a velocity. There is an average velocity if we look over a different time interval, but if we if we change our perspective, how come the velocity changes? Well, what we should do is draw the function, and that's going to show us what's happening in detail. So here's time, and here's position. We know that when time is equal to 0, that x is equal to 0, right? If I stick a t there, and if I stick a 0 for the t there and a 0 for the t there, you get 0. So here's one data point that we know for sure. What's the other 0 of this quadratic? Well, let me just go ahead and figure that out. Where should I go here? If I want x equals 0 and you have 10t minus 2t squared, I can move a 10t over, I can rearrange the formula like that, divide both sides by t. I know that t is not equal to 0 because I'm looking for the other 0. So we have 10 is equal to 2t, so I think t is equal to 5 seconds is what solves that formula. So if I go 1, 2, 3, 4, 5, and then I want to figure out, like, how is this quadratic shaped? Well, I have other data points, right? Because at t equals 1, 2, 3 seconds, I know that the quadratic has a value of um, what was it, 12 meters, right? And I also know that it has a value of 12 meters at 2 seconds, right? So t equals 1, 2. So this is what it looks like. Remember, at t equals 2 seconds and 3 seconds, we both got, for those 2 times, you get 12 meters. So it looks something like this. That's my best drawing. It's supposed to look like a negatively oriented quadratic. That's the best I can do. Um, Average velocity between 0 and 3 seconds, I'll draw as the slope like this, right? So if you count 0 and 3 seconds as your times, then you're going to get 4 meters per second. So the slope of the red line is, 4 meters per second. But if you look at I'll do it in blue now, these two times, 2 and 3 seconds, you get a slope of 0, actually. 0 meters per second. So in other words, the average velocity is not the right way to think about the velocity at any instant. It's just an average over whatever 2 points you choose. So if you're looking here and here, then that's gives you a flat line. But if you're looking, you know, here and here, that gives you a line that's very steep. And so that's the difference between 0 meters per second and 4 meters per second. So average velocity then, which follows this equation, is that it's an average. But if the system is accelerating, then there will be a variety of velocities, and the average will just be the average of those velocities, and it won't always reflect the speed of a system at any given instant. Hello, and welcome to our Physics 135A tutorial video. We're going to talk about a homework problem. This is question 6 on homework 2. So this has to do with a sprinter named Usain Bolt who set a world record for the 100 meters. And before we talk about how the problem is worded, I'd like to just draw what's happening in this problem. So what I'm drawing is a t for time on the horizontal axis, and then velocity on the vertical axis. Now the rules say this is the 100-meter sprint, and you have to start from rest, so the v initial will be 0 meters per second, and the sprinter accelerates from rest to top speed, and we'll call this time t middle, and this is t initial, and then t final will be here. Once the sprinter reaches top speed, we'll call that V maximum. Uh, then the race is over. This velocity indicated up here is V max, like that. I want that to be a dashed line. There we go. And then, so that there's V initial, which is 0, and then there's V max, which we need to find out. The slope of this line is the acceleration, right? The sprinter accelerates to top speed and then stays at a top speed. Let's call x initial 0 meters, and then this time will also correspond to some position down the track when the maximum speed has been reached. We'll call that x middle. We don't know that yet, actually, but we do know here's t final, and this t final corresponds to x final. We do know x final because it's 100 meters. This is a 100-meter sprint. So x final is 100 meters. We don't know x middle. I think that the problem gives t middle as 3 seconds. We know t final, that looks like an F. We know t final is 9.69 seconds, the official time to complete the race. We don't know v max though. We want to find out V max, and to do that, we're going to have to analyze this graph. So uh, you could analyze, for example, this linear portion, noting that V max is just going to be whatever the initial velocity was plus the acceleration times the time, and that time happens to be t middle. We also know that VI is 0 because those are the rules. You have to start from a standing position. Not a standing position, but you have to start still. They're actually loaded into blocks. They used to do it in standing, but now you're crouched. But there is no velocity, and so that's 0. And so V max will just be whatever the acceleration is times t middle. But the problem there is we don't know the acceleration either. So we're trying to get the acceleration and Vmax, but if we knew one, we can get the other. So we need some other relationship that can maybe elucidate what's going on at this point. And so how about the quadratic formula? Let's say the displacement is equal to 1/2 a t middle squared. So to get you from here to there, I'm talking about this displacement, right? Um, Technically, this x-axis is a function of time, but I'm talking about the displacement that takes place between t initial and t middle. T initial is 0, so the delta t that normally goes here just becomes t middle squared. So 1/2 a tm squared plus v initial t middle. But the thing is, v initial is 0, and then what is delta x? Delta x is x middle minus x initial. That's the displacement I'm talking about. 1/2 a t middle squared. X initial is also 0. We're just choosing that to be the location of the origin. So x middle is equal to 1/2 a t middle squared. Now, the thing is, we don't know x middle either. We'd like to know a. We were hoping to get a. We know t middle. We know 1/2, and hopefully we could have calculated it. But the thing is, we don't know the left-hand side of this equation. So let's keep our equations numbered, and maybe they'll be useful if we keep thinking about the rest of the race. Well, the rest of the race is this whole business here, where it's continuing at a constant velocity, and if we're continuing along at constant velocity, then maybe we should be able to use something just like v is equal to delta x over delta t, right? Shouldn't we be able to just analyze it that way? Well, let's do that, but let's do it systematically so that we're accounting for, x middle and x final and, delta t, etc. So the velocity is v max. That's going to be delta x over delta t, but we have to be careful about what these delta x's and delta t's mean. So delta x, we're now talking about the displacement that takes place in this time interval here. So if we have, what's our x final? Well, it's x final, like as in the 100 meters, the end of the race, but our x initial is the middle distance now, because we're talking about, this point to this point, from here to here. And so we're starting that portion of the race at x middle. And that'll be t final minus t middle. And so, well, if we could just solve this whole thing for x middle, maybe we could put it over here and then eliminate, we're not worried about x middle anymore. The goal should be to eliminate things that we don't know in favor of things we do know. That's the whole point of algebra, right? So let's multiply both sides by the delta t in the bottom. So we've got v max times t final minus t middle. We know what t middle is, by the way. It's 3 seconds, and t final is the 9.69 seconds. That'll leave x final minus x middle over there. Let's rearrange the formula so that the x middle is positive and by itself. So x middle will be x final minus v max times t final minus t middle. So let's check the units here. These two distances are in meters, but velocity times time, that's also in distance of meters. So the Vmax would distribute and be multiplying these times, but it's meters per second times seconds. So there's no problem with units there. Now what we're going to do is let's take this and stick it right there. And then that will mean that x middle is gone, right? We'll eliminate it. So we've got 1/2 a t middle squared, which is equal to x final minus v max times t final minus t middle. Now we have two remaining variables that we don't know. We don't know the acceleration, we don't know v max, but now think back to here, right? They're related. So let's eliminate a in favor of v max. So I take this equation and I'll just say a is equal to whatever v max is divided by t middle, and then I'll put that right here for a. So 1/2 v max over t middle times t middle squared, and that's equal to xf minus v max times the quantity of the final time minus the middle time, right? So once again, a is v max over t middle. We've just substituted that for a. A is now gone. Cancel, cancel. So instead of tm squared, it's now just 1 power of tm in the numerator, because it was tm squared divided by tm. So it's like saying x squared divided by x is just x. So we have 1/2 v max t middle, and that's equal to xf minus v max. I'm now going to distribute this v max like that. So v max t f plus v max tm. Why is that last term positive? Because it's two negatives, so negative v max times negative tm is positive tm. Now what do we want to do? We want to get all the v maxes together, factor the v max, and then try to solve for v max. So how about I want them to be positive. Let's see. How about I put the v maxes on the left hand side. So v max tm. I'm going to add v max tf to both sides. So plus v max tf. That will cancel this second term here. So, and then I'll subtract v max tm, and that will leave x f like that. So once again, I added a Vmax TF to both sides, and that would cancel this middle term here, and then another one winds up on the left-hand side. If I subtract Vmax Tm from both sides, that cancels this one and puts a negative Vmax Tm on the left-hand side, and it leaves just XF by itself. Now I can factor Vmax from all terms on the left-hand side, Vmax, and you've got 1/2 Tm minus Tm plus Tf, and then you get XF over here. A half Tm minus a full Tm is negative 1/2, so Vmax Tf minus 1/2 Tm, like that. Right, so these two things are common, like it's a half of something minus a full something, so that's negative a half of that something. And then Tf is just still there, and we have XF. So our maximum velocity reached by the sprinter is XF divided by T final minus 1/2 of Tm. And so V max is equal to, what's XF? Now comes the time to plug in the actual data at the very last second, right? We're plugging in data, so XF is 100 meters, and then T final is 9.69 seconds minus T middle is actually 3 seconds, but we divide by 2, so it's 1.5 seconds. So if we do that, we get an answer. So I'll do 100 divided by 9.69 minus 1.5, and we get about 12.2 meters per second for Vmax. So Vmax is 12.2 meters per second. The relationship between acceleration and Vmax is above, and it's just A is equal to Vmax divided by T middle. We know T middle is 3. So we have 12.2 meters per second divided by 3 meters per second squared. So our overall units work out to be seconds. 12 divided by 3 is 4, and then if it was 2 over 3, that would be 0.67, but there's a factor of 10, so I think it's I'll round to 0.07 meters per second squared. So in other words, our Vmax is above 10 meters per second. It's about 12.2 meters per second, and then the acceleration is about 4 meters per second squared, slightly higher. So that is one answer combo that you find on this problem, where it talks about the sprinter and the world record. So if you're confused about a problem like this, where it seems to have, acceleration and a part with constant velocity, and there's a mixture of ideas, the key is to make a figure, draw a figure that will help you. And as long as your graph or your figure is accurate, you can start to compartmentalize the problem into the first part and the second part, writing equations and then solving those equations with correct data. And that's that leads you to new knowledge that you didn't have before about the maximum velocity in this case, and the acceleration. So thanks for your attention. This has been some homework help of online tutorial video for Physics 135.